Do you ever open Instagram after having a conversation with someone and notice that you see ads related to what you were literally just talking about? It's kind of freaky, right? Truth be told, our private data really just isn't that private. But that doesn't mean that big data has no benefits. For example, Google Maps takes advantage of user location data to calculate where traffic is and redirect us away from jams. As a society, we have to balance the importance of our privacy with the benefits that come out of big data. But what if we could have both? What if there was a way that we could mathematically ensure that our data remain private? Well, let me introduce you to the concept of differential privacy. Differential privacy is a statistical method used to protect sensitive information by injecting randomness into datasets. So what does that mean? Say I'm a researcher conducting a survey to figure out what % of high school students have cheated on an exam. Reasonably, some students may feel worried that their response will be used against them and may even lie as a result. However, we can prevent this by asking them to use the following steps when answering the question. First, flip a coin twice. If it lands on heads the first time, respond with the true answer to the question, regardless of what the second flip is. Otherwise, if it lands on tails the first time, answer based on the second flip. Say yes for heads and no for tails, regardless of what the true answer is. We see that we only get the truth in 3 out of 4 possibilities, meaning that each individual response only has a 75% chance of being accurate. This means that this data can no longer be used against them, even if it gets released. But wait, wasn't half of our data based off the flip of a coin? How can our results ever be accurate? You see, there's one more step, and it involves some math. If we set X to be the % of students who responded that they cheat, and Y to be the % of students who actually cheat, we can use the rules of probability to work backwards to find Y as a function of X. Then we just plug in our survey data and boom, we have an answer. Okay, so we talked about something simple like finding a statistical average, but what about something more complex like machine learning? Well, data scientists apply differential privacy to machine learning by breaking down algorithms and finding locations where they can insert computer-generated noise. Take this portion of an algorithm, for example. We can see it visualized on the whiteboard here. Its job is to perform an operation on every point in a dataset and then count how many of the results are above a certain threshold. As it is not differentially private, but we can make it so by adding noise wherever there is math done. And that is here, here, and here. Oftentimes, this noise comes from the Laplace distribution. You can think of it like a really complex coin that keeps our randomness controlled. One last thing though, even though more noise does mean a more private algorithm, we can't just add as much noise as we want. This is because the more noise we add, the less accurate our algorithm becomes. And the balance of importance between accuracy and privacy will strongly depend on the scenario in which the model is being used. All in all, differential privacy doesn't just protect our data. It also gives scientists new ways to study it. For example, medical records that were once too confidential to study could now be the key to understanding the future of modern medicine. As for now though, only time will tell.